classic boundary layer picture you have, you know that no slip at the surface, there can't be any velocity, so this velocity arrow, again, this is u as a function of y. So, sort of get the idea of this, right, where this is all the fluid that's not moving, right? If it were just plug flow, right, if everything was just this constant velocity profile all along the way, right, this would have arrows filling in, but there's gaps in them. So one thing we pose is how much of this fluid is not moving due to the viscous boundary layer. If I had all plug flow, there'd be more flow rate over the surface of the object. But you can ask the question, how much is not flowing because of that viscous boundary layer? Because of the no slip condition, we have this boundary layer. So how much fluid isn't moving because of that, right? Because of that frictional force that's happening. So here's volumetric flow rate. So take the not flowing, take the width being in and out, and take a little thickness. Or like, right, here's a dy. So take one little sheet of fluid, so that would be all the fluid that's not flowing. So what's not flowing, that's the difference of this straight line of u infinity, because at this point, I get to u infinity. As I get to the boundary layer height, all the velocity becomes constant at just u infinity. So this part is a difference. So that would be minus the actual velocity profile, that's a function, times some sort of width, and then a dy. So that's an integral formulation of what this, right, what's the volumetric flow rate of this shaded part. And then it's sort of the same trick you did where we want to say, I want to write flow rate as a velocity times an area. Well, the area, it would be this width and a scalar number, not an integral. I want to be easy about it. So you do this scalar number, and then you equate with the integral. So these cancel. One last trick, actually, is you actually factor out a u infinity. Zero to the delta, or it could be to infinity. So I'm going to say infinity. But it's actually a delta, extra credit, tell me why. Now these cancel. And then you get something called a displacement thickness. Right? So that's the delta star. It's called the displacement thickness, and it has an integral definition to it. But notice that a couple things. It's not that bad because this thing can be calculated relatively easily if you assume some function that obeys those boundary conditions, right? This isn't that bad if you just assume the function, right? If you assume what the function is before you solve those complex equations. So, right, you should appreciate that. And that's just sort of, right, mathematically, it's a nice term because you can just approximate your boundary layer by assuming a function form and get that bad boy real quickly. The other thing, the classic graph you draw about the displacement thickness is it shows you how to plot these streamlines over a body. So really you've just equated area. So this area and that area are the same. Right, so here is something like that. So these are the same area. Right? And what does that tell you? Well, this just tells you like how the incoming far field flow is also U infinity. This part's U infinity. So it shows how this streamline changes over the body, right? So if you take these, and if you take some sort of airfoil, you will have, maybe it looks like this, right? Where it tells you how a streamline is displaced from the surface as you go over the surface. So it helps you plot these streamlines. A plotting tool. What else do I have on there? Oh, it's also important that the displacement thickness is pointwise. It's not constant throughout whole plate, or right, because the boundary layer is changing. So right, and you can see that if you again boundary layer is a function of x. So you can see the functionality come up that way. Here's the displacement thickness, but you have to keep reminding yourself that it's a function of x because the upper end integral is a function of x. So it's not a constant property. Function of x. So, and that's because as I go down, this thing is increasing. See, so it's growing. This boundary layer grows as we go down. Next is something called the momentum thickness. So the momentum thickness is the same picture, only here's one way to think about it. So again, you draw this picture so many times. Fill that in. U of y is that curvature right there. Again, we'll call this L. Width is in and out of the board. Okay, so usually I looked at a couple books and people just say, and the momentum thickness is defined as this integral. And I understand you guys, right, you all want some motivations for every sort of mathematical statement. So this is my one reason. You can do you can come up with these a couple different ways. But here's my, reasoning of why we write this integral instead of just saying the momentum integral thickness is defined as such. And I'm like, well, why? What? So let's think about the kinetic energy. Sounds like a silly statement. Of the fluid not moving. So let's think about the kinetic energy of this section right here. So that sort of think about this. Think about that little strip, and then think about this little strip. So okay, so this is going forward, and then also the kinetic energy of the not moving. So this little strip of kinetic energy, integral idea, and then this little strip of energy, the difference part to complete the full thing, that kinetic energy. What's the net on that? This is 0. It's not moving. Not moving, we just read it. Okay, you work out the mass terms, a width, a length. So we get one from there. Wait, let me just do it this way. Okay. Okay, so this comes from breaking this up, and you get 2 of these little u squares, and the halves gives you the 1, so there's not the half term in there. You get this. And then what you're saying is move this to the other side. Okay, move to the other side, and you'll say rho this side, you want it to equal just a simple expression where this is the scalar thing I'm trying to come up with. A number, not an integral, a number. And you can see that you can just, since you're saying this is constant, you can pull it out. So, right, you're really sort of integrating up to this. And that we know has to be equal to this side. Where that comes from taking this side, moving it over to the right because it's 0. So I get cancellations. Think about the half. Factor a u infinity squared out, and you'll get the momentum integral. Okay. You go to infinity, but again, you could actually just go to the boundary layer. But up to you. And that is the momentum integral. So we have momentum integral. Right? And then we have the actual boundary layer, which is sort of So these are the 3 sort of main quantities of boundary layer theory. You have a momentum thickness, displacement thickness, which helps you see how large, which helps you visualize the streamlined deviations going over a body, and then you have the actual boundary layer thickness as a function of Reynolds, then this momentum thickness. And there's more on the momentum thickness that involves shear, which we'll talk about.